Section 12.4, we're taking a look today at tangent vectors and normal vectors. I do think that you'll like this section. So to provide a little bit of motivation as to what we're doing in this section, this is the idea. So in designing roads, you would want to avoid curves that are too sharp. So this is three-dimensional kind of curvature stuff, okay? So in this section and then in 12.5, we're going to develop a measure of how much a curve is twisting or turning at any point. So that's what these are going to be doing for us. So three-dimensional curvature. So there's going to be two formulas you're going to see today. The first one's called a unit tangent vector. And the unit tangent vector is so fabulously called capital T of t. Isn't that fantastic? Yeah. And it's the derivative of your position vector, r of t, divided by the magnitude of it. Okay. That makes sense. It's a unit vector, right? Unit tangent vector. So this is the tangent vector. It's a derivative. And then we've created it to be of unit length. So it is much like its name should indicate that it is. All right, so we're going to take a look at an example. We're going to find A, the unit tangent vector. And then B, we're actually going to find a set of parametric equations for the line that's tangent to the curve at T. So A is going to go right back to that definition that we just created for T of T. So we need to find the derivative first of R. And we'll just write it in the component form since it started out that way. So what's the derivative of 3 cosine T? Yep, negative 3 sine T. And then the derivative of 2 sine T? 2 cosine T. Okay, everybody good so far? Yes. Put on those derivative hats again, yeah? And then we're going to evaluate it at pi fourths. So negative 3 sine of pi over 4, and then 2 cosine of pi over 4. All right, so sine and cosine of pi over 4 are square root of 2 over 2. So the first one is going to be negative 3 square root 2 over 2. And the second one would be just square root 2. Exactly. And then we're going to find the magnitude of this. Oops. So we will have the square root of negative 3 square root 2 over 2 squared plus the square root of 2 squared. All right. So the first piece ends up giving me a 9 over 4, 9 over 2, 9 over 2. And the second piece is actually 2. And if we find a common denominator, add the numerators and so forth, we'll end up getting the square root of 13 over 2, or rationalized, it's the square root of 26 over 2, not under the radical. Okay, so we have the two pieces of the tangent, the unit tangent vector that we had defined before. So just as a reminder, I'll write it in here. This is going to be r prime of t over the magnitude of r prime of t. So our two components, and I should say in pi over 4 form, not in t form. Sorry about that. We're doing it at a specific point. We will actually do the one in general in a little while. You're not going to like that near as much. I'm telling you. Okay, pi over 4 here, pi over 4 here. That's kind of messy, but I think we're all right with it. All right, so we had negative 3 square root 2 over 2 and square root 2. And we're dividing by square root 26 over 2, so I'm going to multiply by 2 over square root 26. Okay, so simplifying and so forth, the first time around we're going to get negative 3 square root of 2 over the square root of 26, and then 2 square root 2 over the square root of 26. I want to clean that up a bit, of course, so this is going to reduce right here, the 2, and this is going to be 13 This 2 will give you 13, and then if we rationalize, we're going to get negative 3 square root 13 over 13, and 2, whoops, am I at the edge? I think I am. Sorry about that, let's move this down. And 2 square root 13 over 13. So that is our unit tangent vector at pi over 4. Okay, this is the tangent vector. So for the purposes of what we're about to do, this creates the slopes of the parametric lines that we're going to be working with or finding in part B. Okay, so these are the slopes. So we can call them A and B if you wish, and I will in a moment call the first one A and the first one B. But that's going to be the slopes that I'm going to be working with. So on part B, when I'm finding these parametric equations, they are lines. This is going to be x equals some consistent x1 value. I'll talk about where we're going to get that in a second. And then I've got a times t. The a came from what I had before, or what I found in part A. And then I have y1 plus bt, and b comes from the equations, or the unit tangent vector we just found in the previous part. So how do we get x1, y1? Well, we get x1, y1 by evaluating at the point that we're looking at, because we're doing this at pi over 4. So at pi over 4, we're going to evaluate the original function. So that's 3 cosine of pi over 4. Because it's pi over 4, we're going to get some repeated kind of values like we saw before, right? So 2 sine of pi over 4. So we actually have 3 and then square root 2 over 2, and we just have square root 2 here. And this is actually the point. Well, let me do it differently. Do it the way I did before. This one is x1, and this one is y1. Right, that's the point. This is a position vector, so that's the point at pi over 4. We have the slopes at pi over 4 from the previous part of the problem. So x is equal to 3 square root 2 over 2 minus the slope from the previous slide, which is 3 square root 13 over 13t. And then y, similarly, would be square root 2, and then plus 2 square root 13 over 13t. It's the same thing we did in Calc 1, it's just we're doing it in components, right? We're finding derivatives, we're finding the point, and we're putting them into the equation. It's the equivalent of finding tangent lines from back in Calc 1. Okay. So what we've been doing in everything vectors so far is that we've written all our vectors in terms of the standard unit basis vectors ijk. Sometimes other choices are convenient, though, maybe even more convenient. For example, if you had an aircraft in flight, a better frame of reference would be one that moves with the aircraft. So sometimes we actually don't want to find this in terms of ijk, and so the principal unit normal vector, I think we need a few more adjectives myself, but you go, that's what you got, right? Principal unit normal vector n of t is the unit vector having the same direction as t prime of t, and is defined as follows. So we get our normal vector n of t is the derivative of the unit tangent vector divided by the magnitude, that's what I was looking for, magnitude of the unit tangent vector.
The derivative of the unit tangent?
Yes, that's what I meant to say. Thank you. Too many adjectives there again. The derivative of the unit tangent vector divided by the magnitude of the derivative of the unit tangent vector. There we go. And all of that's only going to work, of course, if we don't have 0 in that denominator. So when we're finding the principal unit tangent vector, I didn't say that right, the principal unit normal vector, it's going to be very similar to what we just did before, but we're going to take this step in addition that's going to find the derivative of what we just found before. But in order to find the derivative, that means we have to have it still in terms of t. So over here, where we evaluated this at pi over 4, we won't be evaluating it at pi over 4 until we get to the very end, because we need to find the derivative first and then evaluate it. So when we're taking a look at doing this in problem number 2, the equation is much similar to what we had before. I don't know, I probably should have used exactly the same one, so it would be a little bit easier for us, but we want to have a little bit more practice, so it's okay. So here's our position vector, right? 2 cosine t, 3 sine t. T equals 0 is our point that we're going to be evaluating at, but we're not going to be evaluating it at any time soon. So the first thing we're going to do is we're going to find the derivative. So that's much like the last problem. So what's the derivative of 2 cosine t? Good, negative 2 sine t. And then the derivative of 3 sine t, 3 cosine t, yeah. Okay, so what we did in the last problem is we evaluated this at t equals 0. But that's not what we're going to do here, because eventually we're going to need to actually take a derivative of something that still has a variable component. So I am still going, however, to find the magnitude. I don't know why I want to keep putting double primes on those. So this is not quite so friendly as the last one, because I don't have constant values. I have variable values. So I have negative 2 sine of t squared plus 3 cosine of t squared. So we're going to square these. So that's going to give me 4 sine squared t plus 9 cosine squared t. So thoughts on how to make that look a little nicer?
So we could take out the 4 minus the sine squared and cosine squared.
Okay, so you're thinking about doing something with the Pythagorean identity, correct? Yeah, we are going to do that. We're not going to take them out exactly, though. Does anybody have another idea? Okay, so completing the square is something we had done before. It's not quite that either.
You could add in signs to get the right numbers to match and then pull out 9.
Okay, that's very close to what we're going to do. So instead of adding them in, we're actually just going to break the 9 cosine squared apart.
Oh, okay, yeah.
So we're going to break apart our 9 cosine squared into 4 and 5 of the cosine squareds. So if I had this written instead as the square root of 4 sine squared t plus 4 cosine squared t, and then add to it the 5 cosine squared t that I broke it apart from, right? Then what will this quantity equal? Hang on, it's slow today. There it is.
4.
Yeah, that's 4. So it may not be a whole lot better than it was before, but it is some better. So this is 4 plus 5 cosine squared t. So this is my magnitude in terms of t, which means I can now find my tangent unit my unit tangent vector. Get this in the right order. And so what we had before up here will be divided by this one right here. So we have, negative 2 sine t over the square root of 4 plus 5 cosine squared of t. And then 3 cosine t over the square root of 4 plus 5 cosine squared t. That is the general form, right, with t in it that we didn't do on the last problem. But we need that, otherwise we're not actually able to progress to the next step. Now, we will need this to find, well, we do need to find this unit tangent vector at t equal to 0, but we needed the general form first. So this right here we will need for in a moment. It's just not, we need this in a moment, but we do want to find this t, did I write? Yeah, of 0. So if I were to put 0 in here, what am I going to have? Because this is actually going to be the answer to this part of the question, part A. What happens when I put it into sine?
0, comma.
Yeah, there's a 0 at the beginning, right? Because sine of 0 is 0. And then for the cosine, I'm going to get what?
3, 1. 3 over 3.
Yeah, it'll be 3 over, and then on the bottom I would have 4 and 5, so that would be square root of 9 or 3, which is 1. So my unit tangent vector is actually the vector 0, 1. So this is actually the answer to the question on part A. So this is my answer on A. This piece, though, I need for later. I need this for B. There's a good delay going on today.
Yeah.
Good delay. Okay, is everybody good so far? Okay, I need to copy this to the next slide so that we don't have to keep flipping back and forth. So I'm going to do that. Okay, so this is where we came from on part B. And we're going to actually find n of t now. So in n of t, I need the derivative of what I just found, which means I need the derivative of this, which is pretty ugly, agreed?
Yes.
Yeah, in fact, it's going to take me 2 lines to write it out, at least it did on my paper, okay? I think that I'm going to be hoping that I can get it across the screen, so I'm going to be kind of going all the way back to the left-hand side to make it work. So we're going to have quotient rules, and what?
Chain rule.
Chain rules. Yeah, there's going to be quotients and chains in there, right? And not only is there going to be a chain rule, but there's going to be a double chain rule, because not only do I have the derivative of the denominator that's got a radical of something, but what's underneath there is also got a squared. It's good, right? It's good.
So exciting. Like derivativecalculator.net.
Nope, that's not going to work.
Okay.
You're not allowed to use that on your test, so we're not going to do it today. All right, cool. All right, so we're going to do the first component first, right? That makes sense. So I need, what? What do I do first? Quotient rule, we haven't done one in a while.
Square the
Whoa.
bottom.
Okay,
I usually start with that.
you start with scoring the bottom. The denominator will be very friendly, won't it? But we start with the
Low times
denominator,
low,
yeah.
high.
Lodi high. So the denominator first. So the denominator is the square root of, over here, 4 plus 5 cosine squared t. I didn't mean that. That's what I want. And I want that times the derivative of the numerator. So what's the derivative of my numerator?
-2 cosine t.
Good. That's definitely the easier half of this one because it doesn't involve the chain rule yet. Quotient rule says I subtract. I'm going to subtract the numerator now. So high, which is -2 sine t. And then the messy part, so I need the derivative of the denominator. So somebody walk me through what's the derivative of this denominator. We'll need it again in a minute, so we only have to get it once.
1/2
Mm-hmm.
times
4,
-5. Oh,
Okay, 4 plus, you're right, 4 plus.
5 cosine squared t times
To the negative.
To the negative 1/2 power, yeah. And then times what?
-5. Oh shoot! No,
times
that's
10 cosine.
Times -10. Okay, so it's negative because I'm going to have the derivative, the sign's coming out. So let me slow down. Okay. Right now we're taking the derivative of the inside piece right here. I'm going to highlight it. Okay. So the derivative of this inside piece, the 2 is going to come down with the 5, making it a 10. So there's going to be a 10 cosine. And then what's the derivative of cosine?
Negative.
Negative sign. So I'm going to put my negative in the front with the 10. Okay. So I'm going to get a negative from the fact that I need the derivative of cosine. And then I'm going to have the cosine because that's the outside function. And then I'm going to have the derivative of cosine, which was the sine, with the negative at front. Okay, so here's the beauty of this, though. So pause and recognize how beautiful it is that somebody gave you t equals 0. Right? So in a minute, a lot of this is going to disappear, right? Why?
Because
Because the sine of 0 is 0. So a lot of these pieces are going to, you're not going to have to clean up the algebra on this, is my point, or the trig. That's the beauty, right? You don't have to mess with the trig and the algebra simplification for it. All right, so all of this then is over what was that, Adeline?
4 plus 5 cosine squared.
Mm-hmm. 4 plus 5 cosine squared t. That is half of what we needed to do, but the second half is easy because we're going to do the same thing. I mean, like, a lot of it is repetition, right? So if I'm doing the second half of this, right, the k component, I, or the j component, I, then j, we're going to have to do the denominator, which is what we did before already. So it's 4 plus 5 cosine squared t times the numerator. So what's the numerator? Man, I'm writing awfully tiny, but I guess I need to. I can write it a little bit bigger, I suppose. Negative 3 sine t. And then have subtraction of my numerator, which is 3 cosine t. And then we already did the next part, right? It's just writing it down again. So we have 1/2. We have 4 plus 5 cosine squared t to the negative 1/2 times negative 10 cosine t, okay, sine t. And all of that, once again, is over the same 4 plus 5 cosine squared t. Okay, so write yourself down a note that says, do not find the magnitude of this with t still in it. Okay, you're going to make yourself, like, go crazy if you try. Like, this would be awful, wouldn't it?
Yep.
Yeah, it would be bad. Okay, that's not what we have to do. The only reason we had to do that over here, right, was because we needed to take a derivative one more step beyond. Are you with me? That's the only reason we did it, right? Like, we didn't do it over here at all, right? We didn't have to because we weren't going a step beyond to do a derivative. There was no need. So at this point, the problem is much like what we did on this problem, where we found the r prime of, of the value, r prime of t right here, and then we evaluated it. And then we took the magnitude of what we evaluated at. That's where we are. We're just doing it now with t prime instead of with r prime. So we're going to take this guy and we're going to evaluate it at 0, which is good news, right? So taking a look at what we have up here, where do you find places where it's going to equal 0? Anywhere where sine is, right. So looking at the first component, the I component, that's right here. And it happens to also be right here, although it doesn't really matter. As long as it's there one time, if I'm multiplying by 0, it's 0. So the second half of this actually eliminates itself. The only piece that actually has to have evaluated at 0 is the piece right here at the beginning. Let me change colors. This piece right here and here. All right, those are the only pieces that I have to put 0 into. Agreed? Okay, and it's not bad because cosine of 0 is 1. So even though it didn't disappear, it became a lot simpler. So on the first piece, if I have the square root of 4 plus 5 times 1, I get
9.
the square root of 9, which is 3, right? So this piece right here, I have the square root of 4 plus 5. I'll write it in just so that you have it written down there so you're not like, where did that 3 come from? And then the other piece was negative 2 times 1. The rest of it went away. Okay, the denominator is still there, though. I still have 4 plus 5, or 5 times 1 if you prefer. Maybe I'll write the times 1 at least in. All right, that's the first component. Not simplified yet, of course, but that is the first component. Second component, similarly, where do you see things going away? Everywhere. It's even better, actually. So we see it go away right here. So that eliminates the first component completely, or the first half of the numerator. And then over here, I actually need that sign of 0 going away over there, so that everything in the second piece is just 0. All right, so I'm going to get square root of 9, which is 3 times negative 2. So that's negative, what did I say, 3 times 2, so that's negative 6. And then the denominator is 9. And that will simplify to
Negative 2/3.
-2/3 and 0. Now, because it's a 0, it's going to feel a little bit funny when I find the next part, because everything's just going to become 1 and 0. That doesn't always happen. That's just happening now, about to happen now, because I've got one of the components is 0. But the next step would be to find the magnitude of this. Show, I have officially run out of space, so hang on a second. All right, so we're going to find, in general, we would find the magnitude now at 0. That should have had a prime. I left off the prime. There we go. Make sure you've got those in there. I left mine off accidentally. So t prime of 0 here then, the magnitude that is, right? I should have the square root of 2/3 squared plus 0 squared, which is obviously just going to be 2/3. And then when I find the principal unit normal vector, right, of 0, because that's what we're working with, which is t prime of 0 over the magnitude of t prime of 0, we're going to get that 2/3 0 divided by 2/3, or in this case we can call it multiplying by 3/2 if you wish, and we're going to get 1, 0. And again, that's just,
Negative 1?
yes, left off my negative, thank you. So if you wish, technically this was a negative as well. I left that one off as well. So -1, 0, there we go. So that's what we would have on our second one. Normally it doesn't do that. We'd have something in both places, of course, that would create my unit vector, but that's a unit vector, so that's okay. All right, questions? Look all right? Okay.